Here's my video report on Lab 6. So the purpose of this lab is to investigate the magnetic induction and eddy currents by analyzing how a falling bar magnet interacts with an aluminum tube and comparing the results to the computational model. In our results, the experiment time of falling was around 1.25 seconds, and in the computational model, it was 0.973 seconds. So here are some of the fundamental physical principles. The Butte-Savart law, which describes the magnetic field generated by a constant electric current. We have Faraday's law, which describes when the magnetic flux or the magnetic field changes with time and the electromotive force is produced. And we also have Newton's second and third law, where F is equal to mass times acceleration. And for every action, there's a equal and opposite reaction. So in our observed model, here are initial conditions of the bark magnet and the stopwatch. The system is the bark magnet and the tube, and the surroundings is everything else. And here's a picture of the setup and a diagram of what each part is. So in our data, the magnet is 0.026 kilograms, and the mu of magnet is 1.4778 amps times meter squared, and that was taken from our previous lab. The tube is 0.3 meters in length, the width is 0.0065, the inner radius is 0.24, and the outer radius is 0.0305. So we did 3 trials, and the average time for all these trials was around 1.253 seconds of the falling magnet. So here's the computational model, the initial conditions, which is just defining the constants that we have. And I also have the geometry of the tube defined and the geometry, or like the mass and mu of magnet defined as well. And this is just the code for creating the tube and the bar magnet. And we also have the initial velocity set to 0 at t equals 0. So here's the rest of the code. We can see the Butte-Savart law being applied. B equals mu naught over 4 pi times qv over magnitude of r squared times r hat. And then we also have the calculation of the magnetic flux, which is d phi over dt. And we also have the calculation of the forces, which is the magnet, or the magnitude of the forces, the force on the ring, and the force on the magnet, and the gravitational force. So here are the results. We get the plot of velocity versus time, and we can see that velocity initially rapidly increases in magnitude, but then it plateaus in the middle, and then towards the end, it starts increasing in magnitude again. And from the computation model, we see that the time of the tube is less than what was found in our observations in the experiment. In the computation model, it was 0.973 seconds. So some similarities and differences, obviously the times are different. The experiment time was longer than the computational time. And assumptions we made for both was that the bark magnet acts as a magnetic dipole to apply the Butte-Savart law. And we also neglect air resistance. And we also say in the experimental model, the only forces involved are magnetic and gravitational, which is the same for computational, but for the experimental model, that's not necessarily true, which we'll discuss in the error portion. So possible sources of error. There are other devices or electronic magnetic devices in the surroundings that could have affected the forces. We're also neglecting the friction that may have happened against the side of the tube. So it may have caused like a longer time than what is expected. And the stopwatch, when we were taking the time, was inconsistent, like starting and ending. That's based on human error in our reaction time and not being super consistent with that. So discussion, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So due to Ohm's law, the induced current in the tube would be much greater, and this would cause a greater magnetic force on the magnet and could counteract the gravitational force, preventing the magnet from even falling. So what if there were holes or slots cut into the tube? How would that affect the ring currents in the model? So the induced current in the aluminum tube would be less, since the holes would disrupt that current, and the magnet would probably fall much faster, as that force is not as strong to counteract the gravitational force. But yeah.